All right, let's talk about chemical reactions. It might seem like a world of pure chaos, but chemists have found some really elegant ways to bring order to it all. Today, we're going to crack that code and see how things you'd never expect are actually connected.
Okay, think about this for a second. A car slowly rusting away, a cake rising in the oven, and a massive coral reef growing under the sea. What on earth could those three things possibly have in common? I mean, they seem completely unrelated, right? Well, it turns out they all share a secret connection, a fundamental chemical pattern that scientists have learned how to spot.
It's kind of like how we classify human interactions. We put labels on things all the time, right? When we share information, we call it communicating. When there's a conflict, we might call it fighting. Well, scientists do the exact same thing with chemistry. They were faced with this endless variety of stuff happening, fizzing, rusting, changing color, and they needed a way to sort it all out.
And the solution they came up with was surprisingly simple. Just classify them. By spotting these common patterns, they could cut through all the noise. They actually managed to boil down a nearly infinite number of reactions into just three main, manageable categories.
And here they are, the big three we're going to break down: precipitation, acid-base, and oxidation reduction, which, thankfully, most people just call redox reactions. Understanding these three is really the key to unlocking how everything from baking to batteries works. So first up, precipitation. And no, I'm not talking about rain. This is something else entirely. It's the almost magical ability to create a solid just by mixing two clear liquids together. This is the very process that builds those incredible coral reefs in the ocean, and it's a super important tool in the chemistry lab. So here's the official definition for you. A precipitation reaction is when you have substances dissolved in a liquid, stuff you can't even see, and they react to form a solid product. And that new solid that just appears out of thin air, that's called a precipitate.
Okay, so let's see this for ourselves. Imagine we have two beakers, and both just look like they're filled with water. Perfectly clear liquids. One of them is potassium iodide. The other is lead nitrate. At this point, nothing to see here, right? Just two clear liquids. But what do you think is gonna happen when we mix them? Are we just gonna end up with a bigger beaker of clear liquid? Or is something a little more dramatic about to go down? And bam, there it is. The instant they mix, a solid materializes right there in the solution. This is our precipitate. In this case, it's lead iodide, or PbI2. It's an almost instantaneous transformation from liquid to solid. Pretty amazing. And get this vibrant yellow solid wasn't just some weird thing in a lab. For a time, it was actually used by artists as a pigment. They called it iodine yellow. It's a perfect example of chemistry creating something beautiful. Okay, on to our second category, acid-base reactions. This is the chemistry that explains the sour taste of a lemon and why an antacid can make your upset stomach feel better. And at its core, it's really all about a simple trade. So here's the crucial point. An acid-base reaction is basically just a transfer, specifically a tiny little particle called a hydrogen ion, which is really just a single proton, gets handed off from one chemical to another. The two players in this little trade are, you guessed it, acids and bases. Acids are the proton donors. They're the ones giving that proton away. A perfect example is the hydrochloric acid, HCl, that's in your stomach. And bases, well, they're the proton acceptors. One gives, the other takes. Simple as that. And when you bring an acid and a base together in a reaction, you get a special process called neutralization. And it's exactly what it sounds like. The two substances basically cancel each other out. And this isn't just theory. It's happening all around you, in your kitchen, in your medicine cabinet. The basic formula is that an acid plus a base gives you a salt plus water. So when you take milk of magnesia, that's a base that's neutralizing your extra stomach acid. And in baking, that baking soda, which is a base, reacts with acidic ingredients like buttermilk. And that reaction releases the carbon dioxide gas that makes your pancakes all fluffy. Now for our third and final category, oxidation reduction, or as everyone calls it, redox. This is the powerhouse. Redox reactions are all about the movement of electrons, and they're the driving force behind some seriously high-energy stuff, like rust, batteries, and even rocket fuel. Okay, the formal definition can sound a little tricky. It says a redox reaction is one where elements change something called their oxidation number. You can just think of the oxidation number as a bookkeeping tool.
It's how chemists keep track of where the electrons are. If that number changes during a reaction, well, you've got a redox reaction.
But let's simplify it. Redox always involves two parts that happen at the exact same time. One substance undergoes oxidation, which is the loss of electrons. The other undergoes reduction, which is the gain of electrons. So one loses electrons, the other gains them. It's a package deal. And if you need an easy way to remember which is which, there's a fantastic little mnemonic, oil rig. Oxidation is loss, reduction is gain. Just remember, oil rig, and you'll always know which way those electrons are moving.
So, how do chemists actually figure out those oxidation numbers? Let's walk through a quick example. Take the molecule H2S. Okay, step 1 is just to look at the molecule. Now, for step 2, we use some chemical rules of thumb. We know that hydrogen almost always has an oxidation number of +1. Since we have 2 hydrogens here, their total is +2. For the final step, we just solve for the unknown. The whole molecule has to be neutral. It has to add up to 0. So, if the hydrogens are a total of +2, the sulfur must be -2 to balance it out. And there you have it.
So that's how chemists track the movement of electrons. But okay, let's pull back from the details for a second. We've covered the 3 main classifications. Now, let's tie it all together and see how these patterns are just woven into the fabric of the world around us.
This table really sums it up perfectly, doesn't it? You've got precipitation, which is all about forming a solid from a solution, like in coral reef formation. Then there's acid-base, which is about transferring a proton, like when you use baking soda. And finally, redox, which is all about shuffling electrons, which powers something as intense as rocket fuel combustion. 3 simple patterns that explain countless complex events. And this is the most important takeaway from all of this. Classification, it isn't just about putting neat labels on things. It's about being able to predict how the world works. By knowing a reaction's type, a chemist can predict if a solid will form, if a gas is going to be released, or just how much energy is involved. It is an incredibly powerful tool for understanding and even shaping our world. So the next time you see a piece of iron rusting, or you're cooking a meal, or even just taking a deep breath, remember these patterns. Because now that you know the basics of precipitation, acid-base, and redox, what other invisible chemical stories can you now see unfolding all around you?